One of the things that we talked about, somebody stayed behind on Tuesday, and we talked about some of the study habits, ideas to be able to do better next time, right? The next exams, because they only get harder from here. Some people really enjoy exams 3 and 4 because it's all diseases, the systems, and so sometimes we do better on those exams. I will tell you, exam 2 is kind of tough because obviously the psychology is a little complicated. So we were talking about some ideas of how to study. And one of the things that I mentioned is that getting together into study groups is really good. Um, being brave enough to actually talk to each other. Again, a lot of times some people think, well, we're in competition for each other to get into those limited spots in nursing school or your program classes. And that's true, but helping lift each other up is always a good thing. So one of the things that I added for the first time ever after teaching for 16 years, I added a discussion board right here, so you can actually get on. It's on both my online and the and your all's class. You click on the discussion right there, and you can actually click here on all sections and just go in there and introduce yourself. This is just for you all, right? I'm not going to go in your monitor. If you want to talk to me, you're on the phone, email, and my office hours and whatnot. But this is an opportunity for you to all just go in there. Individually, if you have questions, hey, does anybody know the answer to this? Does anybody want to get together at the library? I'm going to be studying at 1 o'clock on Tuesday. That's what we use a discussion board for. And that way you can maybe, hopefully, start understanding the material a little bit better. I started realizing when I was thinking about it, one of the best things that I ever had in college was my study parties. Granted, we would get together at 9 o'clock at night and go for an 8 o'clock in the morning exam and study, not sleep at all. That's what we did. But again, nice expecting y'all to do that. But I remember that was some of the most helpful material. One of the most helpful things for me to do in college was to say, okay, let me bounce off ideas to somebody else and sit there and quiz each other. And then hopefully that's better because working in a vacuum by yourself, I know when I read, I'm thinking about dinner, I'm thinking about other things, right? So when I hear all of you say, yeah, I read the chapter, I don't understand, I just can't remember. There's so many distractions in our lives. Just read it sometimes. It's not reading it and then quizzing each other can be a lot more helpful. For the that's something I try to do. So I highly suggest that you utilize the discussion board. Be brave. Be the first one to get on there and say, "Hey, here's my name. Here's how I like to study. Here's where I'm usually at." And I wouldn't necessarily throw your phone numbers up there, but I think all different generations and these are most parts. So, maybe that's more something normal. But it's there for you. Hopefully, that's another tool that you can utilize. As well as a couple of you in this room have already taken the initiative to start putting together. Killian right here is taking the initiative to want to immediately study group 2. So she can be somebody you can get in touch with if you want to be part of that. If anybody else in here wants to form one, great. That's what it's here for. So the discussion board is there for you. It's another option. Use it. Don't use it. How you want to do it. All right, so chapter 14. We're going to finish up chapter 14 today. Chapter 14, unfortunately, for my online class, I forgot to hit the record button on Tuesday, so I don't have the first half of 14. So it's not going to be there. I don't have the time. The room's not available to back here, just record it by myself. So that'll be missing. But the second half will be up there. So we're going to start with the complement system. What we talked about before was all the different parts of the innate system, right? Chapter 14 is all about the innate system. This is what you're born with. So we talk about the skin, we talk about the mucous membrane. Mainly their job is barrier protection, basically putting a wall up, right? Protecting the organism, in this case the human body, from potential bacteria or viruses getting in. So skin, the mucous membranes act in that manner. We also got things like the lysosomes, the lactoferrin, right? Those are just generic enzymes that do things like break down peptidoglycan, or in the case of lactoferrin, binding iron, because both the pathogen as well as the immune system needs iron and zinc to activate enzymes. And then we talked about the way that the cells talk, hear, and see, right? The cytokines, the chemokines, the interleukins, the tumor necrosis factors, all are different chemicals that allow the immune system to be able to talk to each other and be able to coordinate a response to the attack. Now, the next thing that we're covering in chapter 14 is the innate system. Part of the innate system is the complement system. It is the bridge between the innate system and the adaptive. The adaptive system takes upwards of 10 to 14 days to actually come online from the moment that you establish an infection. And you may not know that you're sick for the first 3, 4, 5 days sometimes, depending on the route of infection. Trust me, your complement's gearing up. But at that moment, it's still going to take about 2 weeks for it to come online. So in the meantime, if the infection is already established, it got past the skin, it got past the mucous membranes, then now the complement kicks in. It's still not specific, right? The difference between the innate system and the adaptive system is the innate is non-specific. It's not. It doesn't care if it's an E. coli. It doesn't care if it's salmonella. It doesn't care if it's C. diff. It's just going after generics, right? It's going after those pathogen-associated molecular patterns that we talked about on Tuesday, which is the things like peptidoglycan, things like LPS, Magella, double-stranded RNA, because we don't have double-stranded RNA. And so those things are all things that evolutionarily the immune system has recognized as being bad, and therefore it just goes after them non-specifically. Complement is also non-specific, but it has mechanisms that will try to limit the numbers of bacteria. So complement is only going to go after mainly bacteria. It's not very useful for viruses. And so what's happening here is it's a whole series of proteins. There are some really good YouTube videos available on the complement system, but I don't want you to get lost in the weeds. Right? I'm not going to ask you a dozen questions on the complement on the next exam. But if you just want to get an overall basis of how it's all working in unison, it's a good. There's some good YouTube videos out there, but I'm not covering it here. It's not up on the slides, and it's not going to be important for you to remember for an exam. So these proteins are circulating in the blood, also bathing all over the tissue. These are the complement proteins. The proteins are named in the order they were discovered. So C standing for complement, 1 through 9. And so each of them are going to be important in their own ways. What happens is this is one of those proteins that is not active when it's first produced. So again, a lot of enzymes, a lot of proteins, when they are made by the ribosomes, are actually made in the off position. And so they actually have to be activated. But it's better to have them already there, right? Because we don't have time if you're infected or you have some sort of disease progression happening. We don't have time to wait for the DNA to become upregulated, transcribe the RNA, translate into a protein, get that protein all folded and ready to go. It's better to have these enzymes ready on standby, so when there is an infection, it can immediately go into action. So these proteins are actually going to be there already, all over your body, and when there's an infection, they become activated. The key protein is C3. C3, once it becomes cleaved and splits in half, it is going to cause a snowball effect for all the other proteins. And so C3 can get activated through 3 different pathways. It's about activated through the alternative pathway, and this is going to be when C3b. So when it splits into C3a and C3b. And that's how we know it's split. So when it's still in its inactivated form, it's just C3. When it becomes activated, it splits into C3a and C3b. C3 gets split into C3a and C3b. The C3b has already been activated. It goes and binds to a bacteria, a foreign body, something that's in there that's foreign, right, not self. And it can activate what's called an alternative pathway, which then continues to cascade. The lectin pathway is recognizing those patterns. So one of the patterns that some bacteria have is a sugar called mannose. Mannose ends in OSE, so it's a sugar, right? So mannose is a sugar that's found on some bacteria, and that's something we don't have. We don't have mannose on ourselves. And so just like the other pathogen-associated molecular patterns, mannose is one that automatically triggers C3 to split, or they runs into it. The classical pathway is called classical because it was the original pathway discovered and is the pathway that we think is the most common for complement to get started. So it's activated by antibodies. Antibodies will bind to the antigen, right? Antigen is anything that causes an antibody response, right? So anything to the antigen. Everybody's allergic, not everybody, but a lot of people are allergic to different things. And so, that could be an antigen, it could be a bacteria, it could be some sort of eukaryotic cell, it could be a virus, which is going to interact with the complement system. But typically, when we're talking complement, we're talking about bacteria. All right, so here in this picture, it's a little, because of the way the system's set up here, it's not very large, but I'll walk you through it. If you got them already printed out, or you can see the other screens, it might be easier to look at. But the key to this slide is that every single pathway, so we got the alternative pathway, lactin pathway, and classical pathway, all activating complement in some different way. And notice that the three arrows all come down to C3 convertase. Ends in an A-C, so we know it's an enzyme. So this C3 convertase, what is it doing? It's splitting C3 into A and B. And A becomes a chemokine. Every single protein, when it splits, if it's a C3A or C5A, those are the two big ones, those are chemokines. What are chemokines? Right? Those are the scent signals. Those are the ones that basically are laying down that scent, like I explained on Tuesday, even about like smelling something good, you don't know where it's coming from, you start following that scent. The chemokines are getting laid down. C3A and C5A become chemokines, and so they are going to be in the biggest amounts wherever that infection is, right? So once this happens, why is it happening? Because we've detected an infection. Now what's going to happen is that you're going to have got your site of the infection. Inside infection, you're going to have a lot of C3A and C35 all around it, and it's going to keep getting a little bit more dispersed the further away you get. Macrophages, neutrophils, dendritic cells, and all the different cell types that are part of the immune system are going to follow that scent trail to the side of the infection. Otherwise, they don't know where it is, right? They don't have eyes or ears. They're following that scent trail from the chemokines. So C3A becomes a chemokine and goes out, and of course, like I just said, the majority of it's going to be right outside infection, but it gets dispersed through the blood vessels and whatnot, and then it tracks the other cell types. C3b becomes an opsonization protein. So remember what opsonizing is. Opsonizing is the idea of basically painting the target. Again, because the immune system can't tell the difference necessarily between something that's self and foreign right away, littering the outside of that foreign body, that bacteria, with C3b, is going to now allow the phagocytic cells, the macrophages and dendritic cells, to come recognize that C3b. It may not recognize the bacteria, but it recognizes that C3b. And then it knows that that's something that it needs to phagocytize. So again, it's non-specific. It's not going after Salmonella or E. coli or anything like that. It's going after the C3b that's attached to it. That's how it's able to recognize what it's supposed to be. Yeah, that's all well and good because it helps get the start to those phagocytic cells to start processing those infectious agents, putting them up on the receptors like we talked about in chapter 14. We'll get into more in chapter 15. It's really more part of the adaptive system. And then bring it to the B and T cells. It takes time. Remember, the adaptive system takes a couple weeks. But in the meantime, we can't allow those bacteria to continue to grow, right? Because bacteria are going to multiply every 20 to 30 minutes in an optimal condition. Your body's optimal. And so we're just going to keep doubling. We don't have time to wait 2 weeks. So these other parts of the complement system, the rest of the proteins, C5b through C9, all form what's called a membrane attack complex. So a membrane attack complex is basically like poking a hole in the bacteria. Just like I talked about Tuesday, poking in the hole in some kid in person is never a good thing, right? We have to die. You know, here and the same thing's happening in the bacteria. You poke these holes in them, they die. You know, everything spills out to death. And so these membrane attack complexes are designed to essentially keep the numbers down as best as possible, along with the optimization that's happening to ensure that the bacterial numbers do not get too high before the adaptive system kicks in and finishes them off.
Yeah. So like on the type on I guess like so we need to understand like what a membrane attack complex is, and then we do need to know each of those individual proteins that make that up.
Yeah, I would say like just knowing C5 through C9 is important as part of the membrane attack. Yeah, knowing that the A's are the chemokines, knowing the C3 is the important part.
Okay.
Like I said, you get on and look at YouTube videos. It's going to talk about C1 ERQ or something like that. I think is what it's called. And that's actually like one of the initiation. If it's not even covering it, don't worry about it. So like I said, you get lost in the weeds sometimes watching some of these more complicated YouTube videos. A lot of immunology classes are graduate level classes. So it's much higher than like 200 sophomore class should be. So if you find one that really gets complicated for you and goes beyond what we're talking about here, here are the three major outcomes of complement. We've already kind of covered, right, in the last slide. Opsonization, key. Knowing what is opsonization? We're basically painting the target, right? We're basically painting it for the phagocytic cells to come and bring them in. We're also going to induce an inflammatory response. Those chemokines are, is an inflammatory response. Setting these out and having them diffuse out like this, that's causing an inflammatory response. It's causing the other immune system cells to come to the site of the infection. That's key. But we have to have the inflammatory response to be able to recruit the rest of the cells. As we talked about and we'll continue to talk about throughout the semester, is that sometimes the inflammatory response becomes too low. And it's overwhelming and actually can injure the patient further or even potentially kill them. Right? So sometimes we have to do steroid treatments to dumb down the immune system's response, dumb down the inflammatory response to help the healing process. So the immune system's not perfect. It does make its own mistakes and have capabilities to get around those mistakes. But here, the inflammatory response is key to complement to be able to start recruiting those start recruiting the other immune system cells. And then the third thing that complement does, with those membrane attack complexes, essentially poking the holes in the bacteria and off them right away. But the more damaged cells that we have, the more damaged bacteria we have, that induces more inflammation. So this is where inflammation sometimes gets out of control. So having a bunch of dead bacteria on these membrane attack complexes can even induce more inflammation. The regulation prevents host cells from activating complement. So we have to have ways that we can actually shut complement off. Complement's not necessary, you have to be able to shut it down. Otherwise, you're going to have unnecessary inflammation. And like I said, sometimes that's not a good thing. You don't need inflammation when you don't need it. And so in this case, molecules in the host cell membrane, so our cells, bind regulatory proteins that inactivate C3b. So this keeps C3b from opsonizing cells. What that means, we don't want that to happen. We don't want C3b to be opsonizing our own cells, because then that's going to induce an autoimmune disease. We don't want that. So things like lupus and MS and whatnot, all autoimmune diseases where the immune system has made a mistake and has accidentally started attacking the cell. And so by having these regulatory proteins on the surface of all our cells, prevents C3b from binding and accidentally causing the phagocytic cells. Because again, remember the phagocytic cells, they don't know what the heck they're phagocytizing. All they're doing is phagocytizing whatever's covered in C3b, right? So if it's covered, it's going to get phagocytized. We don't want our self cells to do that. So host cells are going to have a regulatory protein that basically blocks C3b from binding. Foreign cells won't. So then they'll be able to bind and you're going to have it happen. So this is a good thing. We want to have that. What? Well, so if there's no C, Right. What we're trying to do is keep it from getting on cells, which then would basically prevent damage to our cells, right? Damage to cell. All right. So phagocytosis. We've talked about it a bunch. The two big cells that do phagocytosis are going to be the macrophage, who's the big one, and the cells do it also. But what is it? Phago means to eat. Cyto, cell. Cis means the process of, right? So basically the process of the cell eating. And so it could be used for actually what it sounds like, bringing food material. But when we're talking about it from the immune system angle, we're talking about phagocytizing foreign agents. So chemotoxis, this is basically the process of phagocytosis, what the slide is showing us. So what is each step that the macrophage and T cell goes through to phagocytize something? First thing, right? Chemotaxis. We have to get that macrophage or that dendritic cell to the site. We're going to use chemoattractants. So whether it be the complement inflammatory ones like C3A, T5A, it could also be other chemokines and whatnot that could be there to essentially roll or track the phagocytes to the site of the infection. Then we got to recognize and attach. Otherwise, again, this is kind of straightforward, right? You see food in front of you, unless you actually physically pick it up and put it in your mouth, it's useless to you, right? So in this case, same idea, recognition and attachment. We have to bind to whatever it is that we're binding to. So there's a couple different things. You can bind directly to things that it recognizes, like those pathogen-associated molecular patterns. So in this case, receptors that bind mannose. Or it can bind to those opsins, the C3B, C5B, whichever ones it might be that are basically opsonizing. Then we engulf. We've seen a couple pictures of the phagocyte. Essentially, it basically takes its phospholipid bilayer, right? The cell, the macrophage has a phospholipid bilayer around it. It's a cell. And so it basically starts contorting that phospholipid bilayer, where it basically makes a little basket that whatever the foreign agent is, and it just encapsulates it and brings it inside. That phospholipid bilayer never breaks. It does the macrophage bilayer, right? So it has to be able to phagocytize in a way that it doesn't snap the phospholipid bilayer plasma membrane on the outside of the macrophage. And so that's the engulfment. What happens once it engulfs? Remember, once it engulfs, it actually forms a phagosome, right? After phagocytosis. We got our macrophage. Anyway, the shorthand for a macrophage is a M. That's 74. That's a macrophage symbol. So we got your macrophage here, and then it's basically engulfed the bacteria. Bacteria is now inside. That's the engulfment process. Engulfment engulfs. What is this phagosome made up of? This is actually made up of phospholipid bilayer. It was part of cell membrane. The outside. The cell membrane, part of the cell membrane is now making up the shell of that phagosome. And so now it's engulfed with that bacteria. It's just hanging out there. It's not stuck in there. And so what we'll notice as we go through some of the chapters, there's always, like if you're talking about the strategy to the immune system and an infection, some bacteria and other diseases actually prefer to be phagocytized. They want to be. Because then they have capabilities to actually shut down the rest of the macrophage, and then they can grow inside the macrophage. So we'll see some infectious agents actually prefer, as part of their strategy, to get phagocytized. But the majority of them, it's a bad day for them. It basically is injuries for them. And so the next thing that has to happen is that phagosome lysosome fusion occurs. So remember that we have the next step. There's always those lysosomes that are hanging out inside, right? The lysosomes. The lysosomes in here. Okay, and the lysosomes have all kinds of nasty chemicals in them. You want to basically digest the inside the phagosome. But we have them also inside a phospholipid bilayer, right? That's going around the outside of the lysosome. We don't want all those nasty chemicals to be out in the open inside the cytoplasm or the macrophage, when we kill the macrophage, right? So we have to keep it all nice and contained. The next step there, phagosome maturation, phagolysosome formation, is going to be these two things basically come in contact with each other and fuse together. It's not going to be this big, but essentially you get the idea, right? Now these chemicals, these nasty digestion enzymes and other chemicals are now in the same, it's called phagolysosome at this point. It's inside the same vesicle, where now these chemicals are going to go and basically off like that. Yeah. That's key. And so that's the next step, destruction and digestion. Right? So it basically kills it. And then at that point, it floats back up to the cell surface, and then it gets exocytosis. So basically, it just takes out all the waste, all the trash. Basically the pieces and parts of the bacteria that aren't needed anymore inside. So it doesn't really store them; it just throws them out and gets rid of them. Now, some of them are actually going. Some of those macrophages, dendritic cells, when they go through this process, they won't necessarily just exocytose all of everything. They'll also put them up on those receptors again. This is just, imagine an infection that is overwhelming. This infection is, there's lots and lots of bacteria there. Yes, everything's happening all at once. You might have complement happening. You're going to have the adaptive system coming online. You're going to have this type of stuff going on, phagocytosis. It's all the different tools that the immune system has. It's not like it's step 1, step 2, step 3. It's all happening all at once in order to try to knock down those numbers and keep the infection under control. So here's this. Yep. Endocytosis is an umbrella term that talks about bringing anything inside the cell. Phagocytosis is specifically bringing in solids, and so like another variation of endo is penocytosis, and that's basically like the cell drinking. Right. So yeah, so endocytosis is a big umbrella term. Phagocytosis is another. Good question. So here, this is just a picture of that whole process happening, all those steps, right? So we have the chemotaxis happening. We got some of that C5a out there floating around. It's going to start attracting the phagocytes. Got the microbes there. They start getting opsonized. And now here comes that phagosome, and basically the macrophage, whatever it might be, it recognizes those opsonized bacteria, basically engulfs them, right? It's now stuck inside that phagosome. Lysosomes come and bind to those phagosomes, release their digestive enzymes, destroy the bacteria. Bacteria just gets kicked out as waste. Waste also can potentially lead to more inflammation. So it's all part of the process to ultimately get rid of the infection as fast as possible. So as I've already been pointing out, macrophages are one of the big phagocytes. They're scavengers and sentries. So this is one I think I may have mentioned on Tuesday. I always think of it as like a cat that brings in a dead animal and puts it at your feet and goes, "Hey, look what I did for you." And so imagine it's foreign. The macrophage, what it's doing, bringing in those foreign material and bringing it to the immune system, to the B and T cells. And it's the B and T cells' job that we see in chapter 15. It's their job to determine if the macrophage did a good job. And it did a good job. It gives it congratulations, gives it some upregulation signals that then starts the process of the adaptive immune response. If it's a bad macrophage and it part itself back, maybe accidentally, then it gets shut down. It's a bad macrophage, essentially. It tells it, what to do. So here it's phagocytizing everything. It's a scavenger, right? It doesn't care what it is. It's just going to go around grabbing everything. So it could be dead cells, it could be debris, invaders, in this case foreign agents. It's just going around grabbing whatever's there, scavenging it up. There are also sentries, right? We talked about sentries. It's kind of like being the guard that has to walk around Sheridan Hospital downtown. It's a heavy building, walking around looking for any problems. Most of the time, it's never going to see anything, right? But it's there in case there is a problem. So it's not only a scavenger, but it's also a sentry. It's always present in tissues. Can call in reinforcements. Calling in reinforcements to those chemokines. The toll-like receptors on the surface. Remember, toll-like receptors are recognizing the pathogen-associated molecular patterns. The FPGlycan, we talked about before. And it's going to then, if it does run into anything, it's going to release cytokines. Remember, those cytokines are a way that the cells talk to each other. So it's saying, hey, look, I found something that's bad. It starts sending out cytokines to tell the rest of the cells, come, there's a problem here. And then they become activated. So some macrophages actually become what's called activated macrophages. They actually increase in size. They increase in the number of nuclei that they have. Where nuclei is plural for nucleus. Most of the time, they're around a single nucleus, but they do become activated, which then they become larger, multiple nuclei, and so they can do even a bigger, stronger job. We'll talk about that more as we continue into chapter 15, but notice here it says increase the killing of the invaders. Yeah, they become bigger and stronger, they can kill more and do more. They change their name to giant cells at that point. Yeah, they are military use a microscope of like simulated blood that's infected. We'll see the macrophages are always a little bit bigger than the blood cells, but a giant cell is a big, obvious, looking thing like a slide is really, really massive. The T cells, along with the macrophages and giant cells, can form what's called granulomas. And so this is something, if the infection is too great or too complicated for the immune system to figure out, what it does is it forms granulomas. The granulomas are just walling off. So imagine, for instance, inside the lung, tuberculosis, the bacteria that causes tuberculosis, Mycobacterium tuberculei, gets inside the lung and forms an infection. And people can actually live their entire lives, decades, with tuberculosis, and never even know they had it. Actually, the crazy statistic is that about 1/5 of the world population has tuberculosis. And but most of us don't even realize we don't have it here in the United States as much. Overseas, quite a problem, especially in places like India, China, Pakistan areas, large amounts of people infected. But what happens and why they're able to survive for so long, not even knowing they have an infection, is that the macrophages and giant T cells will actually form these granulomas inside the lungs. They'll find that tuberculosis. They can't figure out how to actually clear it. And so they'll put a wall up around it, basically like sealing it off, right? If you got a problem in your house, sometimes people go by homes and then they find out there's problems behind the walls, because somebody decided not to repair it properly, it's kind of all it off to hide it. You have a granuloma that's going on. There's still a problem. There's still active infection happening, but it's been walled off or protected from actually going septic or to continue to grow outside of that granuloma. Lying dormant is a little bit different. That's a bacteria's choice to lie dormant. What we're doing, we're forcing it into dormancy. We're basically putting it in a room and locking the door and saying you're not allowed out. Again, enjoy strategy, right? So some bacteria can then fight free that wall out, especially as you age. So a lot of times people have tuberculosis, they can live for most of their life with it. But as they start aging, getting up in their 60s, 70s, 80s, it breaks out and then they actually have full activated tuberculosis infection because the bacteria was able to get across that granuloma. So granulomas are a good strategy for short term. Right? It's not a good strategy overall, all to basically wall it off and keep it there. The other phagocyte, so we got macrophages, dendritic cells, and neutrophils. Remember, the neutrophils, I always think of them as like the rapid response team. They're the first ones on the scene. They're small, nimble, they can get there as quick as possible, and they're going to be able to do a couple things, right? They can phagocytize, but also remember neutrophils are part of the granulocytes. So they can also basically, the best way to think about it is they puke up the granules on top of the bacteria, on top of the virus, and basically put it on those digestive and let it out. It kills the neutrophil when it does. That's things like a bee with a sting that breaks the stinger off and it dies. But it also just like a bee that does that, it's protecting its hive. The neutrophils doing that, they're protecting the greater good of the human body. Right? They're not necessarily being selfish. It's selfless. So they're going to come in, move in the area, trying to eliminate as fast as possible. Critical role in early stages of inflammation. Like I said, the first one's there. The first one's recruited in from the bloodstream. They're more powerful than the macrophages, but they have very shorter lifespan. Macrophages, they're big groups essentially, and they can come in and they can just start wiping out large amounts by phagocytizing, but they don't have the quick nimble ability to come in and start doing massive damage right away. Macrophages' main job is to come in, phagocytize, bring it to the immune system, the rest of the immune system. Neutrophils, they're coming in, either phagocytizing or dumping the granules and trying to fight off the infection as fast as possible. Macrophage is a scavenger. Yeah, so his question is there differences in what they phagocytize? Absolutely. Yeah, the macrophages, as we pointed out, they're scavengers. They'll phagocytize everything. Neutrophils are going after whatever they've been brought in to attack. They're not necessarily phagocytizing to bring it back to the immune system. They're phagocytizing because what do they have inside them? They're granules, right? Those digestive enzymes. So they're phagocytizing only just to destroy. Macrophages, dendritic cells, are phagocytizing not only to destroy, but also to bring back to T cells. All right, so the inflammatory response. We talked about inflammation a few times already. But this is the whole response, how it actually happens. For the most part. Tissue damage results in inflammation. We talked about this also, and we'll talk about the rest of the semester that sometimes the inflammatory response is actually what causes death in people, what causes major damage in people. It may not be the infectious agent itself and what it's doing. It's the inflammatory response sometimes. It's the worst part. So proposed to contain site of damage. Our purpose is that it contains site of damage. Again, we do not want those infectious agents to get out and go separate. That's the worst thing that can happen for us. So imagine you cut yourself on your leg, and we want that infection, if you got an infection there, we want that infection to stay local. We don't want it to get into the bloodstream and then get able to basically have access to the whole body from there and start causing problems with heart, kidneys, other parts. Sepsis is the worst thing that can happen in a bacterial infection. So keeping it localized and contained is a big part of the inflammatory response's job. Eliminate those invaders and restore tissue function. So try to get the healing process to happen. The healing process really can't happen until the infection is complete. Otherwise, the infection is still there and it's constantly damage happening to the tissue. So it has to actually be cleared before true healing can happen. So what happens in inflammatory? We've all probably had an issue. If you haven't at this point in your age, congrats. But most of us have probably dealt with inflammation at one point or another. You get swelling at the site of infection, right? So if you ever had a cut, you feel it, right? You get pain. It's swollen up. It's red. There's a lot of redness to it because of all the blood coming to that area. You got heat to it because you got a lot of action going on there. So part of the action of all this, macrophages, neutrophils, and all battling. You have a lot of heat exchange happening, so it causes you to feel warm. And you're going to have pain, right? Because there's damage happening, so you're going to have pain associated. And sometimes inflammatory response can be so bad it can dysfunction. Some people maybe get damage to your arm or your fingers or something like that. You may not be able to have full function, but there's a strong inflammatory response happening in those other parts of the body. So the pattern recognition receptors, remember the toll-like receptors are only found on the immune system cells, so the TLR. The NOD-like receptors and that we see on Tuesday, that's what the TLR and NLR help trigger the inflammatory response, right? They recognize, what does that mean? It's recognizing all those patterns, right? So peptide glycan, PS, anything that has been evolutionarily recognized to be bad, it then brings in the inflammatory response. So as it says, detects PAMPs, right? Pathogen-associated molecular patterns, microbes, host cell and release inflammatory mediators, so cytokines. Again, the voice, right? So the voice, the cytokines, then go out and they're saying, hey, there's a big problem. Y'all come over here. It could also be if it's an allergy, right? It could be the eosinophils releasing histamine. The histamine is there to try to destroy whatever. Again, it's just another granular going to destroy whatever it is, but it causes inflammation, right? And if it's had an allergic reaction, you get a massive inflammatory response. I'm definitely allergic to fire ants. With fire ants, I have to go and get an EpiPen. It's just that bad for me. That's because the eosinophils are releasing histamine and causing such a massive inflammatory response that it starts shutting down respiratory, starts shutting down cardio. That's a big problem, if it gets out of control. Again, it's not the fire ant, it's the response, the inflammatory response. So if the blood vessels become damaged, you get an enzymatic cascade that gets activated, meaning coagulation and increased permeability of the vessels. And that becomes where all the blood basically get internal bleeding issues. Really bad. But as part of that process of inflammation, we want that to happen because a lot of the immune system cells are just floating around in the blood vessel. And so by having some permeability occur in the blood vessels, it allows those immune system cells to sneak across the blood vessel and get to the site of infection. So when the inflammatory response is under control, it's actually a good thing to have that permeability in the blood vessels to allow the immune system cells to get across. So it's all a cascade event, like we talked about. There's multiple steps that go there. But the key is what we just talked about just now, dilation of the small blood vessels. So dilating, opening them up, allow these bigger cells that normally would be able to get across the blood vessel, you now be able to sneak through those holes that are formed. That's where you're going to get the heat and redness, right? Because you've got increased blood flow. And you're going to get a little bit of internal bleeding happening there. Again, if it's controlled, it's fine, part of the process. But when it's out of control, especially in sepsis, where the bacteria is basically being pumped through the blood, the immune system's constantly trying to chase it. It's permeable, it's basically permeating the entire blood, all the blood vessels. So you end up having blood pressure drop because all the blood is leaking out all over the body. You get blood pressure drop, and it leads to shock. Shock leads to death. And so sepsis is always a bad thing because that inflammatory response is trying to chase that bacteria. Inflammatory responses are only good when it's local. Migration of leukocytes from the bloodstream to tissue, what I just said, so the endothelial cells, so the cells that are part of the blood vessel, will actually grab the immune system cells, grab those phagocytes, and slow them down. Otherwise, they're flying through blood and they can't really stop. So they're going at those sites of infection as part of the inflammatory response. The endothelial cells are going to grab those phagocytes, say, hey, get over here and get on the other side of the vessel because we have a problem happening. And so the phagocyte will then squeeze through the vessel. That process is called diakinesis. That's there for you. I don't ask any questions on it. But I do ask questions on how the phagocytes actually get to the other side. The clotting factors will wall off the side of the infection. Again, so like forming a granuloma, but not quite the same. But we're going to wall off that side of the infection to minimize any chance of those bacteria or whatever the infection agent is to go second. So when you have pus, if you have bad enough infection, you get that white pus that comes out. What is that white pus? It's just basically dead neutrophils and tissue debris, bacterial debris, all that action that's happening at the side of the infection. That white pus that you get is just all the dead material. So we have two types of inflammation: acute. Acute's good. That's what we need to happen. Acute, when we use the word acute, we mean short period of time. So it's a short-term. Macrophages clean up the damage by digesting all the waste, all the dead cells, all the debris, cleans it up. The inflammation goes away. The site of the infection starts to heal. Good. Acute inflammation is fine. If acute fails, and again, that strategy, the bacteria may have a way to, or the virus, whatever it may have a way to fight off the macrophages, then potentially We can have chronic inflammation. Chronic inflammation is going to be where the giant cells of macrophages form, giant cells start to accumulate, and you start forming those granulomas. And at that point, it's almost like an emergency situation, like we said, throwing them in a locked room. I don't know how to deal with you. I'm just throwing you in a room and locking the door, forming that granuloma. So that's going to ultimately be the sign of chronic infection, chronic inflammation. And at that point, usually that's going to cause somebody to have long-term problems too. You have chronic inflammation happening. So this is a good picture demonstrating the idea of getting a puncture wound. So in this case, somebody stepped on some sort of, I don't know what they call it, doesn't really tell us, a nail, something that caused a puncture to the skin. So we've gotten past the skin. Remember, the skin is a key part of the innate system, right? It's there as a barrier. Well, when you have something that punctures right through it, you basically have gone right past there, right? The skin juices at that point puncture right through it. Now we're in the sterile area of the tissue underneath the skin. If that thing that you just got punctured by had bacteria on it, now the bacteria just got a free ride right into the sterile area. Right past the skin barrier and right into the sterile area. That bacteria is going to start to multiply, loving it. But remember, macrophages are just kind of hanging out, right? They're sentinels. They're just kind of hanging out in different areas of the body. And so in this case, you got your resident macrophage just hanging out there going, hey, all right, it's going to be an exciting day today. And so it's going to start phagocytizing the bacteria. It's going to start releasing cytokines to ultimately start bringing in more of the immune system cells. So here you can see the blood vessel. You can see that there's always, anytime we take a smear of blood, there's always a small percentage of neutrophils and macrophages in it. So any given moment, if I did a blood smear on anybody here, we would see neutrophils and macrophages. So they're always floating around in the blood, just in very small amounts. So here they're already floating around in there. Because of that release of the inflammatory chemicals, those cytokines, chemokines, it's going to cause dilation of the blood vessel. And what's happening then, remember, monocytes are, you have to go back and look at what we talked about on Tuesday. Monocytes are what they're called, what macrophages are called, when they're just circulating around the blood. Right? So once they get switched over and they actually get, where their diapedesis is happening, where they're getting crossing over the dilated blood vessels, their name switches over to macrophages while they're in the blood and monocytes. And so now we got a bunch of macrophages there. Notice what they're doing. They're starting to clean up that. Major bacterial infection. This moment here is when we're going to have the most amount of pain, most amount of redness. That's when the battle is really happening. And then slowly but surely, the macrophages, if everything's working right, the macrophages and neutrophils that got accumulated there are going to basically take care of the bacteria, clean them up, get rid of it, and ultimately the infection is going to come under control and healing can happen in the best case scenarios. Worst case scenarios, that battle's lost, the bacteria continue to multiply, continue to outpace the recruitment of the phagocytes, and that's going to require then the adaptive system. The adaptive system is going to come in and try to actually add some more of the complement has to get involved. Lots of other things can happen, but in a good situation, if it's just a minor infection, inflammatory response can take care of that recruiting and macrophage and neutrophils. So the damaging effects, we've already talked about. This is a slide that's everybody in your home studying. Damaging effects of inflammation process. I like this analogy. Process is like a fire sprinkler system. Great, protect the building, but there's a lot of damage that happens from flooding, right? That happens. A lot of furniture. If we had sprinklers go off from here, all the electronics would be ruined, right? But ultimately, money is saved by the building not burning down completely. Same thing with inflammation. It can keep the disease or whatever the infectious agent is from spreading. It keeps it contained, but it's going to damage that part of the body. Right? The body's going to damage in some sort of way. So, what is the damage being caused from? caused from the enzymes and all the different toxic compounds that the neutrophils are releasing and the macrophages are releasing. It's going to damage not only the infectious agent, but it's also going to damage the tissue, the host. If it's in a delicate system, we'll end the semester talking about nervous system diseases, mainly meningitis. And why is meningitis so deadly? Because there's so little room for error inside the spinal column and inside the brain. So inside the skull, there's not much room. And so if you have major inflammatory response happening in the brain, that's going to cause major damage to the brain and usually causes death. Untreated, somebody has meningitis, the mortality rate for people that are untreated is almost 100% because the body can't handle inflammatory response happening in these delicate areas of the body. But luckily, it's really difficult for bacteria to actually get. Usually it's going to shut down before then. So unfortunately, some people contract meningitis, but it's so rare that when it does happen, it makes a huge difference. We have meningitis infection. But, there's always a small percentage. It's usually going to be in elderly people that their immune system is already weakening. It can also be college age, but it's usually below the 70s. Cell death and inflammatory process. Remember we talked about the difference between apoptosis and necrosis. Apoptosis is controlled cell death. We call it controlled cell suicide. Programmed cell death. That's the way to think about it. But if you see about apoptosis or anything about apoptosis, think about it as being controlled. When it's controlled, it does not trigger inflammatory response. It's good. You want it because every day, every minute of every day, there's different cells in your body that are naturally coming to the end of the lifespan, and they die and they're being replaced by other cells that come into cell cycle and replace them. But the ones that die, we don't want them triggering an inflammatory response. So we have adapted apoptosis in a way to let those cells die without causing an inflammatory response. Pyropoptosis is when pattern recognition receptors are triggered, cells may undergo cell death and cause an inflammatory response. So it can be necrosis. Necrosis is when the cells are dying uncontrolled. And so some infectious agents can cause necrosis to occur too. Whenever we use the word pyro, right, we always think fire, right? Well, and so somebody's like a pyromaniac, somebody wants to set fires. In this case, when we're using pyro, that means it's causing inflammatory response to heat. Inflammation, that's what a pyro is being used here. And fever, right? We're down chapter 14. Fever. Fever is an important part of the host defense mechanism, right? We think a lot when I ask people generically, what do you think fever is caused by? They're like, oh, it's caused by being sick. I've got a virus and I've got a fever. Truthfully, the reality is, a fever is actually a part of your defense mechanism. It's actually part of your immune system. Not the bacteria, the virus that's causing you to have a fever. It's your immune system's response that causes the fever. And so it's a strong indicator of infectious disease, especially bacterial. Most viruses don't cause a fever. If you have a fever, it's probably a bacterial infection. Again, remember there's always exceptions to every rule. So it's usually a pretty good indicator somebody has a fever that's actually a bacterial infection. It's a temperature regulation center in the brain. Is going to control what our normal temperature is. And so remember, everything in medicine, allied health, is going to be in Celsius. And so body temperature in Celsius is 37 degrees. But we also talk about Fahrenheit, right around that range. We raise it up. We raise that during an infection to these things that are causing the fever. So anything that causes a fever, it gets the name pyrogen. Remember, just like antigen, antibody generator. Pyrogen, it's a fever generator. So in this case, bacteria are fever generators, pyrogens, and that's going to cause the fever to cause your temperature to go up inside your body. And what that's doing is it's doing two things. One, remember your body is optimal conditions for infection and for bacteria. Bacteria love our body. They're essentially adapted to it. You're the ones that cause disease. And so that's when they can replicate the fastest. We increase our temperature just a little bit. That slows down that bacteria. It's no longer optimal for the bacteria. So it slows down their ability to replicate. Also, what a fever is doing is it's going to speed up. Because, if you had this thing about, like, if you're trying to speed up dinner, you might go turn the oven up an extra few degrees, right? That speeds it up a little bit. In this case, adding heat, which you may remember from freshman biology, adding heat increases the speed of enzymes. It increases the speed of things that can happen. So we're slowing down the bacteria's ability to multiply at its optimal rate because we've increased the temperature and now it's outside of its optimal rate zone. So it's not going to be able to replicate as fast. And we're also speeding up the immune system. So fevers are actually good. So when somebody takes like Tylenol or ibuprofen or some other generic drugs to bring down a fever, you're actually increasing the amount of time it needs to heal the fever is there on purpose. So if you can tolerate the fever, it's always best to let it stay. Now again, fevers can get out of control, right? Somebody's got to come in with a fever 104, 105. Yeah, we need to break it down because now we're dealing with proteins inside your body. The enzymes and the proteins are actually starting to denature and fall apart and causing damage. When proteins fall apart and cause damage, what happens? So there's a point where fevers can be done. So if you're just sitting at home and you take your temp and you got a 99.9 or 100 something, don't take Tylenol, don't take any medicine because that's actually there to help benefit you. You're actually bringing your temperature down. Bacteria will go more faster, right? Slowing down your ability to heal. So moderate temperature increases, like it says here, moderate temperature rise, increased rates of enzymes, enhances the inflammatory response, helps that whole system go. Now, I'm not saying that if you're sitting there miserable and you can't handle life because your fever is so making you so miserable, take this. You're just taking it because, oh no, I got a fever. That's what we call palliative care, right? Just taking care of the symptoms. So if you need palliative care, cool. If not, remember that the fever is actually there for a reason. All right, so got 15 minutes left, but I don't feel like pulling up chapter 15. It'll take 5 minutes or so. Pull up, so we'll jump a little bit early. Do you have any questions? Okay, question.
Well, I've heard that younger kids or children can have a higher symptom. Because they would say that they can withstand higher temperatures compared to
I've never really studied much of pediatrics, so I'm not doubting it's true. I'm curious myself.
I was thinking maybe because of the immune system fighting more because it's less built up.
Well, that could be it. That was my first thought. That's actually what I had thinking first, in my mind was that because the immune system in children is still building up. It may just be that it has to be under control. They call it cycle high adult phases of infection. Basically found it.
Child, delivery, 1 or 2 months, you're a baby.
Question. I'll try and ask the nutrition that's true. My child was yeah, questions?
Yeah. What did you say?
Anything that induces the fever. Usually it's bacteria. Those are the two most important. Complements are a lot more complicated than what I talked about. When I learned it, it was actually like 2 chapters of material. So there's a lot more, but I want you to focus on focuses on C3A and 5A being the chemokines. B are the opsonizing.